We will now talk about the process of antidifferentiation, and in particular, its applications to the functions of position, velocity, and acceleration. We will start by watching a video by Felix Baumgartner trying to attempt to break the speed of sound in a free fall.
Release. If you're scared, because there's a bunch of finishing. Yeah, we all feel the same. I'm going over. Generate. Speeds.
There are two interesting points in the video that I'd like to draw your attention to. First of all, it's pretty clearly visible that the Earth is in fact round, so I just want to clear up any misconceptions about the fact that it is an almost perfect sphere. And second, you notice that right after somebody declares Felix is stable, they start clapping, and that is before he lands, and that is because they were really worried about him actually going into a spin, because the amount of gravitational, like centrifugal forces, might have caused him to black out, and he was the only person in charge of his own parachute. So that point in the video is where they were sure that he was actually going to make it back to Earth alive. Now, I wanted to show you the graphs of the altitude or the position and the speed or velocity of Felix's fall to discuss that different graphs can be useful for different kinds of information. So first of all, these graphs are derivatives of each other, right? So the altitude function is as computed, but the speed function is really the derivative of the position function. So here we have a graph and its derivative. The speed of sound, which he was trying to break, is anywhere between 330 and 340 meters per second, depending on the temperature of the air surrounding it. So 331, for example, here corresponds to 0 degrees Celsius, whereas 343 corresponds to about the room temperature of 23 degrees Celsius. So the natural question to ask really is, did he actually achieve the speed of sound in his fall? For that, we're going to look at the speed function, and here we can see that the highest point, or the max speed, occurs just above the 350 mark. So yes, we can be pretty certain that he did actually break the sound barrier. But what is really surprising about this graph is right after he manages to hit that peak speed, his speed decreases drastically. So what happened? We didn't notice that in the video, and he pulls his parachute way later. So why such a sudden drop in speed? Let's take a look at what we can figure out here. So this occurred just about at 50 seconds, or maybe just a little bit before, when he was going at the speed of just around 350 meters per second. Now, again, the speed doesn't tell us much, but let's see what that corresponds to on the altitude graph. And here, just before 50 seconds, is approximately 30,000 meters, or 30 kilometers. What happens about 30 kilometers above Earth is there is no atmosphere above that. The 30 kilometers is when you actually enter troposphere with oxygen. Oxygen is great for life because that's what we breathe, but it's not good for free-falling objects because it creates drag due to air resistance. So this, in fact, had to be accounted for when mathematicians had to figure out how high does the Felix's little capsule have to go up to so he can jump off of it, so he can reach the speed of sound without atmosphere surrounding him. Because in our atmosphere, he wouldn't be able to reach that as a maximum speed. So this highlights that things like altitude and speed and acceleration are extremely important in computations that surround any kind of space explorations. Let's now talk about a more general setup of uniform motion with constant acceleration, which occurs exactly in the process of dropping the ball, and the only force acting on that object being gravity. Now, instead of going through this myself, I'm going to let our textbook author, Leah Keshe, show you how to derive these things. In that, I also would like to draw your attention to the fact that the textbook for the course is a great resource that has all of the material that we're covering, except for several applications, but all of the theoretical background, lots of different types of examples, lots of different exercises, as well as links to different types of videos as well. So please check it out, and off to Leah we go.
Let's recall that if we go from a displacement to a velocity to an acceleration, this is the process of differentiation. If we go the other way, this is anti-differentiation. In fact, in the example we do now, we're going to start with information about the acceleration and deduce something about both the velocities and the displacement. So we're going to assume what's called uniformly accelerated motion, namely that the acceleration at any given time is constant, and in fact, we'll denote it as minus g, where g here stands for the acceleration due to gravity. In other words, we're going to be thinking of a ball that's falling under the force of gravity and accelerating at that uniform rate. The derivative of the velocity, which recall is the same as the acceleration, is equal to minus g. From that, we can deduce something about the velocity itself. Now, let's think for a minute. What sort of function did we have to start off with in order that when we differentiate it, we get minus g? Well, clearly it should be something of the form minus g times t, because of course when we differentiate this, we'll get simply this coefficient minus g. In fact, there could be any other additive constant, because the derivative of that constant would vanish when we differentiate. Now, what does this constant mean? Let's look at the fact that if we plug in t equals 0, we get v of 0 equal to c, and so therefore c is actually denoting the initial velocity of the object. That initial velocity could be positive or negative. In our case, perhaps the ball is moving upwards. Let's see what happens as a result. Okay, now from the velocity, we can say something about the displacement. So let's recall, first of all, that the derivative of the displacement is the same as the velocity, and therefore we can say something about the displacement itself by finding a function whose derivative is this quantity. Now, in order to be able to get this, when we differentiate the displacement, we have to have one higher power for the variable. So when we differentiate t squared, we'll get the power t to the 1. But we'll also get a factor of 2 that comes out. To account for that, we're going to divide this by 2. And so altogether, we'll have minus g over 2 t squared, remembering that now this is v0. The second part, we'll need the function v0t in order to give us this. And finally, we may have another constant k that appears here, which again, when differentiated, vanishes to give us the velocity. About this constant, we could say the following. If we look at the displacement at time 0, these two terms vanish, and we're left with y at time 0 equals k. We're going to denote that by the quantity y0 for initial displacement. So altogether, we've been able to figure out both the velocity and the displacement.
So just to quickly recap, the process of going from the position to the velocity to the acceleration is differentiation. The process of going backwards is the acceleration. So we've seen in the video how Leah has derived all the formulas that you will likely see in a physics class, and how these are nothing but antiderivatives of each other in the process of simply applying a power and anti-power rule and making sure that you calculate the corresponding constants. Now for our next application, let's take a look at constant acceleration on the moon. There, we don't even have to talk about our simplified model of assuming no air resistance and therefore no drag, because there's no atmosphere on the moon. So our simplified model of assuming that the forces of gravity are the only forces acting upon an object are actually all of the assumptions that we need to make. So first, let's take a look at the video of how David Scott drops a feather and a hammer on the surface of the moon.
In my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon, and I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
Now, the reason that the astronaut points out that the feather is that of a falcon is that falcon is actually the fastest bird on Earth and the fastest in the free fall form. So they've managed to bring a feather up there just to run one of these experiments on the surface of the moon. Now, in all of the word problems, I strongly encourage you to, where possible, draw a little bit of a graphical illustration of what is going on. You don't need any artistic skills, and trust me, I don't have very many, but just producing a little picture will sometimes help you figure out exactly what is happening in the situation. So in this case, we have an astronaut who is dropping a feather and a hammer from about, we're told, 4 feet of height. Okay, we know the acceleration on the moon due to gravity, and we would like to figure out when does that object, when do either of those objects hit the actual surface of the moon. So, as in the previous derivation, nothing has changed here except for the gravity constant is different, but we will start with the acceleration, which is minus 5.2, and we should move in to the velocity function, which we then know to be minus 5.2t plus the initial velocity. Now we saw that the astronaut was not throwing the objects onto the surface of the moon, but was rather just dropping them, so initial velocity in this case will be 0. We then take one more step back in antidifferentiation for displacement or position function. In this case, it's the height, and we can see that this is going to be 5.2 t squared over 2 plus, according to the most general formula, plus initial velocity and the time plus the initial height. Now, the initial velocity was 0, so this middle term is 0, but the initial height, as suggested by our little picture here, is 4 feet above ground, so my initial height will be 4 feet. So now, overall, the height function is given by minus 5.2 t squared over 2 plus 4. And the question is asking, when does the object, either of the objects, when do they both hit the surface of the moon? Now, the surface of the moon here is, of course, our ground zero. So the question becomes, when does this function equal to 0? So we need to solve for h of t being 0. Okay, and this is just a quadratic equation and a fairly straightforward one at that. So I encourage you to actually do these calculations by yourself. I should warn you, though, that for a quadratic equation, you should get 2 roots, unless they're repeated. So here, in fact, we will get 2 roots, and it will be plus minus 1.24, and the time was measured in seconds. Now notice that I'm getting a positive and the negative, and then of course we're speaking about time, so the negative root should be rejected. However, the positive one is the one that remains. And so the answer to our question, how long does it take for the objects to hit the surface, the ground, is 1.24 seconds.
Before we do yet another application, let's take a look at the algebraic underpinnings of going backwards in differentiation, or anti-deriving something. So here I have a table. I have a column for functions that is empty so far, and I have a column for derivatives. Not sure what happened to the notation here. There we go. So here, instead of giving you a function and asking for a derivative, we're going to try to go backwards. We know what the derivative is, and we would like to know what the function that it came from actually can be. This is something that was already in Leah's video on some level. Here we're trying to derive a more general rules that will be reverse of power rules. So please pause here for a minute and try to actually fill out this table so that you can see how antidifferentiation works firsthand. Now, thinking of the first line here, we're going to start with some function whose derivative is going to be 3. What could that function have been in the first place? What do I have to differentiate in order to get a constant? Well, through some trial and error, I can see that it's going to be 3x. In this case, x is our variable of choice. For the next one, I would like to get x as my derivative. Now we know that the power rule brings down the power by 1. So it makes sense that we will think that x squared is a good starting point. Unfortunately, if I take a derivative of x squared, the 2 has to come down to the front, and then I subtract 1 from the power. So the answer here will be 2x, not just x. Fortunately, though, constants are easy to fix. Remember that when we take derivatives, we simply rewrite our constants. So if I know that I will be acquiring 2 in the process, the thing that I can complement it with is including 1/2 right away. This process of antidifferentiation can always be checked by differentiation. So now that this is my educated guess in terms of producing x as a derivative, let's actually try it. If I take a derivative of 1/2 x squared, what's going to happen is the power will come down to the front. We're keeping the constant. So I'll have 1/2 times 2, which is just 1, and then the power will get reduced by 1. Indeed producing my x value. If this is where you got stumbled when doing this for yourself, pause now and see whether with this kind of logic you can proceed through the rest of these examples. So next up is x to the 4th. We know that we are starting with something here, that the power rule, we subtract 1 from the power of, and we're going to want to see a 4. So obviously we would like to start with x to the 5th. Now that will give us the correct power, but not the correct constant in the front, because if I differentiate x to the 5th, I will see 5 come down to the front, and I would like to see just 1. So in order for me to avoid that, I will place 1/5 in the front. And in fact, we can already see a rule forming simply from these two. If my derivative is a power of x, then the function that it came from, or antiderivative, is the same power of x increased by 1 with the corresponding constant in the front. Okay, so something to remember later on. Next, we have 2x to 100. So we already kind of know what to do with the powers. So let's deal with x to 100 first. We're going to want to start with a power 1 more. And then we're going to have to balance out the actual constant. So we will divide by 101 so that when it comes down to the front as a part of the power rule, we will not get the coefficient we don't want. However, here for the first time, we have a different coefficient, 2, that has to come from somewhere. So here we simply need to reintroduce it back into our equation. So this will acquire a 2 on the top. Now we are getting into powers that are not just positive integers. So here we have -3. But remember, the power rule, being very powerful, works on any kind of actual powers. So here, the same logic will apply. In order for me to end up with -3, I should have started with a power 1 less than that, -2. So that when I subtract 1 from the power, I end up with the one that I have here. And again, I'm going to need to actually adjust for the coefficient this will produce. This will bring -2 down to the front. So I need to divide by -1/2. Okay, what about this next example here? 1 over x. The way to deal with it is to turn it into a power rule, in which case it's going to be x to power negative 1, and then see if our logic applies again. So here, what do I have? What do I have to start with in order for me to produce x to the negative 1? I should have started with x to power 0, because then subtracting 1 will lead me to x to the negative 1. But x to power 0 is just 1. And I know that the derivative of 1 is 0, not the reciprocal function. So that doesn't quite work. And that is, in fact, the only time that the anti-power rule cannot be applied. It can be applied for any other power except for negative 1, specifically because we run into this issue here. For negative fractional powers, the rule holds just the same. For me to acquire negative a third, I should have started with x to power 2/3. And I notice again that that would mean that I will then be subtracting 1, and I will end up with negative 1/3 as desired. But now I need a coefficient here to balance out the fact that I will be bringing 2/3 down. So this will be 1 divided by 2/3, or if I'm very proficient with fractions in my head, I can notice right away that this will actually flip the fraction and will be 3/2. So the anti-power rule is pretty clear how to apply. But then the thing that we haven't quite noticed yet is the types of things that we should look out for in general. So let's take a look at the very first function and its derivative. So I started with the function 3x, and that produced the derivative of 3. But the thing is, all the constants will be taken away in the differentiation. So if I start with the function 3x plus 7, its derivative will also be just 3, because I only will really take a derivative of this portion that will produce something non-trivial. The derivative of 7 will be 0, and it won't be noticeable here. Okay, I can actually start with anything here, so 3x minus 13, right? This will still give me the derivative equals 3. I can start with my main function and any single constant, and it will produce the exact same derivative. So that leads us to the general observation that the antiderivative can only be determined up to a constant. Okay, because again, constant will go away in the differentiation. So constant can be anything in the original function. So that means that in my table here, I will have a plus c plus a constant added to any one of these functions, and my table will still be true. A derivative of 1/2 x squared plus any constant, any number at all, will still be just x. So I need to always be mindful of the fact that there is these constants lurking all over the place. And this, in fact, is what makes antiderivative not the antiderivative, but an antiderivative, okay? Because we can have any constant, it's actually an entire family of functions whose derivatives are always f of x, okay? So here we can also note our power rule being reversed in an anti-power rule type of fashion. I'm not gonna write anti-power rule, that's not its official name. We can simply say that an antiderivative of a power function, so of something like x to power n, is, what was the rule? We add 1 to the power and we divide in a coefficient by that new power. And this works for anything except for the power of -1. Okay, so we cannot start with the power of -1 here and apply the exact same rule. Okay, so now because we have an antiderivative, it means that generally the general antiderivative of this function will actually be up to a constant. So generally, antiderivative of our power function isn't quite as simple as just x to power n plus 1 over n plus 1, but rather we also have to add some kind of constant, Don't forget it cannot be equal to -1. Now, the things that help us determine this constant, similarly to the way that Leah did it in her video, are other conditions that are given to us alongside of the function itself. These are often called initial conditions. So here is a very straightforward example of the initial conditions and the derivative-antiderivative relation. So we're going back to the Galileo dropping the ball from the Tower of Pisa. We would like to know the velocity of the ball and the height of a ball at some time t. So what do we have that is given? It seems that we have very little actual information at our disposal. We know that the height of the tower is 55 meters. We know that he simply drops a ball and doesn't throw it with any kind of force. And the other thing we know is the acceleration due to gravity. So the only thing that we actually have given is the acceleration function, which is minus 9.8 meters per second squared. Notice that this problem uses meters, so we're going to stick with the metric system. Now, if I have the acceleration function and I am wondering what the velocity and the heights are, I will have to follow through the exact same steps as in Leah's video. So I encourage you to pause here and go through the exact same steps with the new information about the Tower of Pisa that you are given here. So the relationship is position is to velocity, what velocity is to acceleration, and if we're following the arrows in the left to right direction here, we're going to take derivatives. So taking the derivative of the position will produce the velocity, taking the derivative of velocity will produce acceleration. And in order for us to move in the other direction, we're going to have to take antiderivatives. Okay, so this is exactly what we're going to do in this question here. Again, you actually have all the tools to go through this question by yourself, and I encourage you to do just that. So given the acceleration, we are able to go one step backwards to the velocity function. So the velocity function is the antiderivative of the acceleration. So that means I need to think about what did I have to take a derivative of to get minus 9.8. Now my variable here is called t, so I'm going to stick to t as in time variable. What would produce just a constant as the answer? And here it's pretty clear that what I needed to take a derivative of was minus 9.8t. However, it's an antiderivative, so it's always determined up to a constant that I better remember. At every step here, though, if possible, I would like to actually figure out what my constant in this particular case is. So Galileo, standing here on top of the Tower of Pisa, is dropping the balls, which means that the initial velocity at time 0 of each ball is simply 0, because he's not throwing them down with any kind of force. The initial velocity is at a standstill, 0. So that means I can plug this information into this formula here. The initial velocity is 0 when the time is 0. So what am I going to get? I get 0 equals minus 9.8 times 0 plus a constant. So in this case, my constant c is actually equal to 0. So here, what I have is that my velocity function is equal to minus 9.8t. In general, however, we have to remember that we computed the velocity as 9.8t plus some constant, and this constant was actually determined by the initial velocity of our object. So this is what we in general call v0, okay, where v0 is the initial velocity. Okay, and this is the most general formula for dropping or free-falling object here, where we actually can now account for throwing it down with some kind of initial velocity as well. Now, next up in our example, so we found the velocity at time t. Here it is. Next up, we would like to find the height of the ball. So we have the velocity, we would like to know the position. And again, this is governed by the antiderivative law here. So we're going to remember that the height function, let's call it h of t for height, is going to be antiderivative of the velocity. So that means that now I have to look at my velocity function, for my case, this one here, and take an antiderivative of that. This is where we get to apply our anti-power rule. I will keep my original constant, minus 9.8, and then I have to take an antiderivative of t. Remember, we have to increase the power by 1 and divide by that number. So t squared over 2. Always remember that you can check your calculations by taking derivative of your suggested answer. So if I take a derivative of that, will I get this back or not? I should, but will I? So if I take a derivative, I keep the constants alone, then I bring the power down, so this 2 will cancel out with this 2, and I reduce it by 1, therefore getting the exact same expression as I want. One more little nuance is the fact that this now is going to have to be a general antiderivative, which means that it also comes with some kind of constant. Let's call it k, because we don't want to reuse the same constant here. C was already solved to be 0. Okay, so my general function of height is this. Now I know that the initial height is the height of the tower itself, which is 55 meters. So I know that at 0 meters, my ball was at height 55, and so I can use this information here. The height was 55 at time 0, so altogether I will get, well, let me write this out, so minus 9.8 over 2 at time 0 plus k, of course not equal to 0, but rather equal to 55, which is the height. And so here, solving for k, I can see that k has to be equal to 55. This entire term will be 0, k will be equal to 55. So in my case here, I have that the height function is equal to, what do I have? I have this expression, but now I know that k is 55. So minus 9.8 t squared over 2 plus 55. This is what happens in my case. In general, though, because I'm able to actually say something in general at this case, what I would be doing is taking the antiderivative of this expression, right? In my case, the initial velocity was 0, so I didn't have this term. But if I wanted to compute the position in the most generality, I'll be using this formula. So my first part, minus 9.8 t, is going to produce the same antiderivative. So I'm going to still have minus 9.8 t squared over 2. But now I would be taking the derivative of v naught, some constant. Sorry, antiderivative of v naught, some constant v naught. So an antiderivative of a constant will be the same constant, but multiplied by the variable t. And then I also have to have this same constant being present. Now this constant, as you noticed, turned out to be exact same as the initial height. And that's what it will be in the general case too. So this is the most generalized version of the height function. The acceleration due to gravity, the time squared divided by 2, initial velocity v naught multiplied by the time at which I am going to calculate the position of my object, in this case a ball, and then I have to also add up the initial position or the initial height. Okay, for those of you taking physics, you are given these formulas to work with, and now you know where they come from, which is directly from the acceleration due to gravity and anti-differentiation laws. Now back to applications. The one thing in the videos that we haven't touched upon yet are the falcons. So remember that the astronauts brought a falcon feather with them and decided to drop that on the surface of the moon. They are claimed to be the fastest animals on Earth, and who better tell us about it than Sir David Attenborough?
To watch a bird that has evolved into one of the world's most skillful hunters, I've come to Italy and the city of Rome. There's a bird that flies over these roofs that finds its prey not on the ground, but in the air. And it owes its success to its speed. In fact, it's said to be the fastest moving animal on Earth, the peregrine. Peregrines hunt other birds. Many different kinds of birds now live in cities, attracted by the food and shelter that is so easily found here. And a tall building like this is an ideal lookout for a hunter. Flying prey can move in any direction it chooses, so a hunter has to be both fast and agile if it's to get a meal. A peregrine's wings have a very special shape. They're pointed and swept back. If wings have a blunt end, air will swirl over that end, forming trails of turbulence. These act like brakes, slowing a bird down. But pointed wings shrink that edge and so reduce the turbulence. Pulling the wings back towards the body makes the bird even more streamlined. And speed is crucial to a peregrine's success. It also has acute vision that enables it to spot prey over a mile away. And for the peregrines that hunt in Rome, these birds are prime targets. Starlings. They too are fast flyers, and their smaller size makes them even more maneuverable. So, to catch a starling, a peregrine must be even faster. And in order to gain speed and surprise, it attacks from above. First, it climbs. When it sees a group of its potential prey, it turns, dives, and accelerates by beating its wings. The starlings are still unaware of the danger hurtling towards them. Finally, the peregrine draws its wings back. This is called the stoop, a superb streamlined shape that slices through the air. Now it can reach speeds of over 200 miles an hour. As it nears its target, it opens its wings to slow its descent and makes its final lunge.
So now that we've seen how peregrine falcons actually fly and hunt, we can talk about some of the physics and math behind their acceleration and their speed. So we're going to assume that their downward acceleration is due to gravity alone. Okay, so in the video you've noticed that Sir David Attenborough mentioned that at the beginning, when the falcon turns around to start on the free fall, it actually flaps its wing to get some additional speed. We're going to assume that that is not the case. We're also going to assume that there's no air resistance because, again, this is a simplified model, and introducing drag into the system is something that we're going to have to wait to do until Calculus 2. What we would like to know is how far would a falcon have to free fall to achieve a speed of 300 kilometers an hour? Okay, very high speed here. They are the fastest birds on Earth. In the video, you heard it mentioned that they can achieve speeds up to 200 miles per hour. We're going to see at what height does the falcon have to start free falling in order to achieve the speed of 300 kilometers per hour. So let's sketch a very rough picture of what's happening. So I have a bird, I have a falcon here. Let's say this is approximately my falcon with its wings. Again, doesn't have to be a great picture. There's his claws coming forward. It's got two of them. Okay, and this is the ground somewhere. So the question here is, at which point, at which height does the free fall have to start in order to achieve towards the ground the speed of 300 kilometers an hour? The only thing we know here is, again, the downward acceleration. Now in this question, just to be a little bit different, let's point our axis down together with the falcon's fall so that the acceleration is in the same direction as the movement of the bird. And we know that the acceleration is due to gravity alone at 9.8 meters per second squared. The one thing that we notice right away is the differences in units. My acceleration is always given in meters per second squared or feet per second squared, but the speed I'm interested in here is in kilometers per hour. So the first thing we're going to do is transfer this into meters per second. And 300 kilometers per hour is approximately 83.3 meters per second. I'm not going to go through the calculations how to actually do that. Unit conversion is not something that we're going to get hung up on in this course. So, first of all, I need to actually know the distance, how far. I'm starting with acceleration. I remember from the previous slides that the antiderivative of acceleration is velocity, and antiderivative of that is the actual distance. So I know I'm going to have to go through this intermediate step of computing the actual velocity. Now, that's fairly straightforward, the velocity being the antiderivative of the acceleration is 9.8 t. And of course, you remember the constant, 0, here because there is no initial velocity. So I'm going to set this to be 0 since no initial velocity is present. The bird simply turns around and starts falling. So now I need to figure out at what point in time is the velocity equal to what I would like it to be equal, right? So let's write that down because this is not quite the same as in the previous actual questions. First of all, we need to figure out at what time is falcon's velocity equal to 83.3 meters per second. Now, so far, this is pretty straightforward because the velocity formula has, of course, the velocity, which we know what we want it to be, and the time. So I can simply plug everything in. So 83.3 is equal to 9.8 t, and I can solve for the time. In this case, it's approximately 8.5 seconds after the beginning of the free fall. And now I have to figure out what was the distance that falcon actually fell to achieve this velocity, knowing that it took him 8.5 seconds to do so. So we went from acceleration to velocity. Now we have to bring it all the way down to the height formula by taking the antiderivative of our velocity. So 9.8 t squared over 2 plus some other constant k. Okay, now we are going to take, remember we're pointing the axis down, so the falcon is our origin and our axis is pointing down, so the height at which it starts falling is actually equal to 0. So k is going to be 0 since initial height is at the position of the falcon itself, is at falcon's original position that we're taking as the origin. Okay, so now I have a formula that connects the height and the time. And I know that he reaches the velocity I'm interested in time 8.5 seconds. So that means that the height in 8.5 seconds is actually what I am after here. If I plug this in, I'm going to get approximately 354 meters. So that means that in order to achieve the velocity of 300 kilometers per hour or 83.3 meters per second, the falcon has to fly free fall 354 meters. This is quite a bit, right? And so this also shows that the initial flapping of the bird's wings to achieve non-trivial initial velocity does help it a lot in accelerating during the free fall. But the really neat thing is that in this one lecture, we have managed to tie together the concepts that were developed by Galileo Galilei in what sort of seems like ages ago at this point, as well as space travel, as well as the moon exploration, as well as the fastest animal and human on Earth, all within the same mathematical structures. That is what makes math such a cool discipline, is that we can talk about all of these kinds of things all in the same time. Now, the last example in this lecture, now that the inspirational, let's say, part is over, is going to be the general setup for what we call initial value problems. This is the most generalized version of what we have seen so far with the acceleration, velocity, and position transitioning of the functions with the antidifferentiation connections. What we have here isn't a particular gravity or anything like that. We simply have a function's derivative given to us. So remember that this means the derivative. So I can rewrite that as y prime equals 5t. And then I'm also given what we call an initial condition, something that gives me a particular point on my function, not the derivative, but the function itself, that I actually can use. So if I start with this equation that we call a differential equation because it involves a derivative, I need to apply anti-differentiation. I will need to calculate the antiderivative in order to obtain the function back. Okay, so if I take an antiderivative, on the left I have just y. The antiderivative of 5t, according to our anti-power rule, is 5t squared plus 2, t squared over 2 plus a constant. Now, this constant in the problems before, when it came to heights and velocities, we have actually derived from the context, right? The height, for example, in the Tower of Pisa problem was 55 because that's how tall the Tower of Pisa is, and that's where the initial drop was from. The velocities, the initial velocities of all the things we've talked about so far have been 0 because we've been simply dropping them and not throwing them down. But for the general case, the constant will be solved for using the actual initial condition. Okay, so we're going to use this information to solve for C. Use initial condition to actually solve for C. Okay, so we are simply going to plug that in. Now this says that y of 1, so that means that t is equal to 1. And when t is equal to 1, y is equal to 4. Okay, so overall, y of 1 equals to 4 means that here I have y is equal to 4 and t is equal to 1, which of course allows me to solve for c. So from here, I'm going to skip some of the calculations. C is 1.5. So overall, in the end, what we have is the solution that I started with here. This is a more general solution, but my particular solution is 5t squared over 2 plus the constant that I actually managed to figure out, 1.5. Okay, and that is what normally will be the end of the initial value problem, a solution that does not involve any constants at all, just the variable that we started with. One thing to note here, though, is that we went from an equation that involved a derivative to the general solution that involved a constant to a particular solution that involved only the variables themselves. If you think about this graphically, what this is saying is the derivative is some function, in this case 5t. What the general solution suggests is that we have an entire family of functions up to a constant whose derivative actually satisfies this equation. In this case, these are parabolas, right? T squared, 5/2 t squared. So these are actually parabolas looking up. So let's sketch ourselves one rough graph of what these might look like. So these are parabolas, 5t squared over 2 plus a constant. So parabolas that are looking up, but we don't quite know which height they're at, right? This C is going to show us the transformation of the parabola, the vertical transformation of it, right? So it's either shifted up or shifted down, okay? All of these parabolas, we call a family of these functions, all satisfy this equation and therefore this differential equation. The initial condition gives us a point on the function that we want. So out of all of these parabolas, the initial condition fixes the one parabola, y of 1 is equal to 4, the one parabola that we want. Okay? And that's what allows us to find a particular solution for our one particular case. And instead of having infinitely many of these solutions, we have just the one. So in this case, on my picture, this one parabola here is going to be the one that both satisfies our differential equation and satisfies our initial condition. Okay, this is a general setup for the initial value problems that we're going to see in this course. The general approaches to these types of problems is something that we're going to explore in more depth in classes like Math 118, Calculus 2 for Life Sciences, and Math 112, Calculus 2.